Good evening and welcome to a new course about ordinary differential equations. This course is about a new topic, the last topic in this course, numerical methods for solving ordinary differential equations. Numerical methods are those methods that are used to concretely compute the values of the solutions by brute force without computing the solution itself at a discrete set of points. So instead of finding a formula for the solution, we just compute its values at the points that are interesting for us, and maybe by interpolation, we can extend these formulas to an interval. For the numerical methods that we study here, the solution is also computed approximately with an error, which can, however, be estimated and be made acceptably small. And usually, numerical methods are used by computer. So numerical methods are usually employed by computer to graph the solution of an ordinary differential equation when it cannot find the formula for the solution. The simplest and best known numerical method for solving ordinary differential equations is Euler's method. It is not widely used in practice because the errors are too large, but let's start by understanding Euler's method, and then I will present a couple more methods. So this is the setup for using Euler's method. We consider a first-order ordinary differential equation y prime is equal to some function of x and y with an initial condition y at the point x0 is equal to y0. Then we compute the solution at a discrete set of points forming an arithmetic progression with a usually fixed step size h. So we start at x0 where the initial condition is given, and then we compute the solution at the points x0 plus h, x0 plus 2h, x0 plus 3h, etc. So for Euler's method, usually the step size is fixed, but of course nothing prevents us from using a variable step size. Okay. So the general formula for these points at which we are going to use Euler's method, so for these grid points, is xn is equal to x plus nh. Okay, and we'll denote by yn the approximate value of the solution y of xn that we will be computing at the point xn. So yn will be an approximation for the true value y of xn. And our method works step by step. At each point xn plus 1 in our grid, we will compute the solution based on its value at the previous point xn. So Euler's method uses this simplest possible approximation to compute the solution at the next grid point, namely y of x plus h for any differentiable function y is approximately equal to y of x plus h times y prime of x. So this right-hand side formula describes the tangent line to the graph of the function, and this says that for small values of h, the function does not deviate too much from the tangent line to its graph. So we can use this formula for small values of h to approximate the function at a point y of x plus h, so at the point x plus h, by knowing its value at the point x and the value of its derivative at the point x. And in our case, the derivative of the solution y of x is given by the ordinary differential equation. So y prime of x is, as I said on the previous slide, is some function of x and y. So then, using this approximation, we can say that the value of y at the next point in the grid, xn plus 1, is, so xn plus 1 is xn plus h. So then we can approximate it by y of xn plus h times y prime of xn. And y prime of xn is equal to f of xn and y of xn by the ordinary differential equation. However, we don't have the value of y of xn, we just have the approximate value yn. So we make a further approximation, and we are going to approximate y of xn plus 1 by yn plus h times f of xn and yn. So the errors accumulate because at the previous stage, y of xn is not exactly equal to yn. At this stage, y of xn plus 1 is not exactly equal to yn plus 1. We have both the error from the previous stage and the new error that we made by using this linear approximation. Anyway, hopefully, if the step size h is sufficiently small, then the errors can be kept under control. And we'll do a little bit of error analysis just a little bit later. In any case, this is Euler's method for computing the solution numerically. So we start at a point x0 with the initial value y0, and then we compute the values successively at points xn, such that xn is x0 plus nh. And the formula for going from each step to the next step is xn plus 1 is xn plus h. So we add one more h to go to the next point in the grid at which we are computing the function numerically. And the approximate value at that point is yn plus 1 is yn plus h times f of xn and yn, where f is whatever function we have in our ordinary differential equation. Okay, so let's consider a concrete example. Let's consider this very simple equation that we already know how to solve. Y prime is equal to 2y with the initial condition y of 0 is equal to 1. And we want to use Euler's method to compute an approximate value for y of 1. So what we'll do is we'll use a grid of points on the interval 0, 1, and we'll compute an approximate value on each point in this grid, and starting with 0, where we already know the value, and ending with 1. And we'll divide the interval 0, 1 into steps of equal size. The more steps we use, the better the approximation will be, as we'll see. So Euler's method says that each next value, so the value yn plus 1 at the point xn plus 1, is equal to yn plus h times f of xn and yn. And here h is the step size. In our case, the function f of xn and yn, so the function f is this very simple function 2y. So f of x and y is 2y. So when we plug in xn and yn, notice that the right-hand side here actually does not depend on xn. It only depends on, will only depend on yn. So, so instead of f of xn and yn, we should write 2yn. Okay, so the starting point is x0 equals 0, and the starting value at that point is y0 is equal to 1. And the simplest thing that we could do, but also the least accurate thing that we could do, is to go through the whole interval in one step. So make a step equal to the length of the interval. So let's choose the step size age is equal to 1, and then starting at x0 equals 0, y0 is equal to 1, then the next step will already take us to the end of the interval and the value that we want to compute. So the next point in the grid will be 0 plus the step size, which is 1. And the value at that point, the approximate value at that point, will be y0 plus the step size times 2y0. So since y0 is 1 and age is also 1, we get 3. So the approximate value of y of 1 is this y1 here, which is 3. The disadvantage is that the error is really bad. Because you use the step size that is too large, the error is really bad. Okay, so what if we use a smaller step size? So instead of taking one step to go through the whole interval, we use 2 steps. So this means we now are going to use a grid with 3 points, 0, 0.5, and 1. So the step size is 0.5, and we start from 0. The first step is 0.5. The second step is 1. Okay, so then what is the value of the solution computed in this manner? So the first approximate value is y1, which is y0 plus the step size times 2y0. So since y0 is 1, we get 1 plus 0.5 times 2, so we get 2. So this would be an approximate value for y at the point 0.5. And this is how these numerical methods work. We use this value again in the next step. So each step builds upon the previous step. So the next step, we are supposed to compute the value of the solution at 1, and the approximate value is y2 is equal to y1 plus 0.5 times 2y1. So each step only depends on the previous step. And at the previous step, we computed y1 to be 2. So now we have 2 plus 0.5 times 2 times 2. So this is 4. Okay, so now 4 is the approximate value of the solution that we computed by using Euler's method with 2 steps on the interval 0, 1. And so y2 is the approximate value of y of 1 that we computed by this method. However, the step size of 0.5 is still much too large, and this is nowhere near the actual value of the solution. But in any case, this is the approximate value that we get. To get more accurate results, we need to significantly lower the step size. This isn't really practical to be done by humans, though I think people did this with electric adding and counting machines and maybe even pen and paper before the computers were invented. So nowadays, this is mostly done by computers. So we're only going to do these examples with a very small number of steps and a very large step size just for demonstration purposes. So this is the only computation that I will do with a relatively small step size. So let's choose a step size of 0.1. This means we'll need 10 steps to go from 0 to 1. We start with the initial point 0, so then next point will be 0.1, after that 0.2, 0.3, 0.4, all the way up to 1. So using steps of size 0.1. And at each step, the value of the solution only depends on the previous step. So for example, the approximate value y3 only depends on the value of the solution at the previous step, y2. And if we had a function here that depended on x as well, then it would also depend on x2. But since we have 2y, then it only depends on y2. So in Euler's method, y3 is equal to y2 plus h times 2y2. And h is 0.1 in this computation. So we go from each step to the next step. For example, if y3 is 1.728 approximately, then we take y3, and y4 is y3 plus 0.1 times 2y3, which is approximately 2.07. And we do this 10 times, and we end up with the approximate value y10, which is the approximate value at the point 1, which we reached in 10 steps. So the approximate value of y of 1 that we got by Euler's method with 10 steps is 6.191. So if we keep lowering the step size, then we get increasingly more accurate values. So if we have a step size of 0.05, it will take us 20 steps to get y of 1, and the approximate value will be 6.73. If we take 100 steps, so if the step size is 1 over 100 to go from 0 to 1, then y of 1 is approximately 7.24. And in 1,000 steps, then the approximate value is 7.37. So the more steps we use, it turns out that we get a better and more accurate value, but of course, this requires more computational times and more computing resources. And the actual value is y of 1 is equal to e squared, which is approximately 7.389. So we got an accurate value with just the first two decimals. This is not great because we had to use 1,000 steps just to get the first two digits correct. And this is why people don't often use Euler's method in practice. Right, so here's a more complicated example. Again, for Euler's method, let's try to solve the initial value problem y prime is equal to x squared minus xy squared with the initial condition y of 2 is minus 1. And let's estimate y of 3 using Euler's method with step size 0.25, so 1/4. So we start at the point 2, and we want to get an approximate value for y of 3 with a step size of 0.25. This means we're going to need 4 steps to get from 2 to 3. Okay, so the computation that gives the next value at each step is, so the next point, xn plus 1, is xn plus the step size. So we start with 2, the next point will be 2.25. After that, the next point will be 2.5, then 2.75, and then 3. So each time we go to the next point by adding the step size 0.25, and the next approximate value will be yn plus 1 is equal to yn plus h times f of xn and yn. So what is f here? F of x and y is x squared minus xy squared. So f of xn and yn is xn squared minus xn yn squared. So at each step, we plug in the values obtained at the previous step, starting with the initial conditions. So x0 is 2, y0 is minus 1. And then for y1, well, so it's going to be y0, which is minus 1, plus the step size, which is 0.25, times, well, so x0 squared, which is 2 squared, minus 2, so that's x0 again, times y0 squared, so that's minus 1 squared. So this turns out to be minus 0.5. And we keep doing this. So in order to compute y2, we use the values computed at step 1. In order to compute y3, we use the values computed at step 2. And in order to compute y4, we use the values computed at step 3. And eventually, we end up with this value, approximately 1.238. And because the step size 0.25 is too large, then this computation is only for demonstration purposes. So the actual value is quite far from this. It's 1.695. So let's try to estimate the error in Euler's method in order to see what step size we have to use in order to get the error no bigger than an acceptable margin of error. So this is called error analysis, and you don't really have to know how this is done in this course, but this is the basis of all of these numerical methods. So people trust that they work because they can control the size of the error, and they can prove that by using a sufficiently small step size, they get a sufficiently good approximation to the actual solution. So the source of error in Euler's method is the error that we committed when we use this linear approximation, y of x plus h is approximately equal to y of x plus h times y prime of x. So this formula is only an approximation. This would be true if y were a linear function. In general, for differentiable functions, this is only an approximation. So how big is the error? How big is the difference between the left-hand side and the right-hand side? And the general answer to these sorts of questions is given by Taylor's formula. So this is the general case that says how we can, this formula says how we can approximate a function knowing its value at a point and its derivatives at a point. So if we know y of x, y prime of x, y double prime of x, or as many derivatives as we want up to the nth derivative of the function at the point x, then y of x plus h is approximately equal to y of x plus h, y prime of x plus h squared over 2, y double prime of x plus etc. all the way to plus h to the n over n factorial times the nth derivative of y at the point x. And then we get a precise expression for the error term. So one of the ways to express the error, this is called Taylor's formula with Lagrange error term. So Lagrange's formula for the error term is h to the n plus 1 over n plus 1 factorial times the n plus 1th derivative of y at some point c between x and x plus h. So I guess the important thing is that when we use the nth order Taylor expansion, then the error is of size h to the power n plus 1. So for example, when we use the linear approximation, the error is of size h squared. And it also depends on the n plus 1th derivative of the function. And this error is small if h is close to 0. And the more derivatives that we use in this approximation, the smaller the remainder it will be. So the smaller the error will be. In our case, we have that y of x plus h is equal to y of x plus h times y prime of x plus this error term, which is h squared over 2 times the second derivative of y at some point between x and x plus h. So in our case, the unknown function that we are trying to estimate in this manner, y, will be twice differentiable if the function f in the ordinary differential equation is differentiable. So, for example, if this function x squared minus xy squared is differentiable, then the solution function y will be twice differentiable. So since we usually solve equations with smooth coefficients, then usually this is not a problem. So the solution in general is twice differentiable, and this formula for the error makes sense. So it's h squared over 2 times the second derivative of y at some point. And in order to estimate the error, we're just going to make the simplifying assumption that the second derivative is bounded by some constant, let's call it capital M. And then the error in the approximation is bounded by this constant m over 2 times h squared. So these errors are committed at each step when we use Euler's method, and then they get compounded with each successive step. So an error committed at step 1 gets increased, gets magnified at step 2, and gets magnified even further at step 3. So in other words, the error will increase exponentially with the number of steps. Okay, so let's try to actually estimate the error. Let En be the size of the error of at the nth step. So the difference between the approximate computed value yn and the actual value of the solution at y of xn, and then in absolute value. So we're just computing the absolute value of the error. So then a computation using Taylor's formula shows that the error at the step n plus 1 is less than or equal than the error at step n plus h, which is the step size, times capital K, which is a constant that we use to bound the first order derivatives of f. So actually, K is a bound for partial f over partial y. Okay, so then this is the way the error propagates from the previous step, and then we get an extra error of size h squared over 2 times capital M from the current step. So each error is at most equal to some contribution from the previous step. So the errors from the previous step propagate and increase, plus a contribution from the current step. Okay, so then by induction, by expressing each error as a function of the previous error, and starting from a value of E0 equal to 0, because at the starting point the error is 0, because there we know the initial conditions. There is no error at the starting point. We get that the error at the nth step is less than or equal than this sum. So 1 plus hk plus 1 plus hk squared plus 0 plus 1 plus hk to the power n minus 1 times h squared over 2 times capital N. So it turns out that this is a formula for the error at the nth step based on chaining the previous formulas. So expressing each error as a function of the previous error. So this is the sum of a geometric progression, this parenthesis, and it's equal to 1 plus hk raised to the power n minus 1 over hk. So we notice that 1h cancels, h here cancels with h squared here, and we get 1 plus hk raised to the power n minus 1 times m over 2k times h. So let's see what is the error over an interval of size L over which we have used n steps of equal size. So then the step size is the length of the interval L divided by the number of steps, n. Okay, so then from the formula on the previous page, I have expressed one of the ages as L over n. So we get 1 plus lk over n raised to the power n minus 1 times m over 2k times h. But this formula, 1 plus 2k over n raised to the power n, in the limit when n is very large, actually converges to e to the power lk. And whenever x is a positive number, actually 1 plus x over n to the power n is less than e to the x. So it turns out that this parenthesis can be bounded in a way that does not depend on the number of steps. It's just less than e raised to the power lk. So we get this bound that the error is less than e to the power lk times m over 2k times h. So we notice that the error increases exponentially with the length of the interval L. And the error also increases as a linear function of the step size h. So if we use twice as many steps for the same interval, then we can reduce the error by half. If we use 100 times as many steps, then we reduce the error to 1 over 100 of what it was. At the same time, if we use this method over a very long interval, then the error will increase exponentially with the size of the interval. So these sorts of numerical methods for which the error is less than a constant times the step size are called first order methods. So this means if we use, let's say, 100 times as many steps, then we can expect to improve the error by a factor of 100. However, if instead of using this linear approximation that we use for Euler's method, if instead of that we use a higher order Taylor expansion, so if we use the Taylor's formula with more derivatives, then we can improve the error. And higher order numerical methods take advantage of this fact. So a numerical method of order n is one for which the error is less than a constant times h to the n, where h is the step size. So suppose we have a method of order 2, and we use 100 times as many steps over a fixed interval, then the error, we can expect it to improve by a factor of 10,000. So second order methods, or in general higher order methods, should be better than first order methods. And the higher the order of the method, the better it should be from the point of view of getting a more accurate expression for the solution. However, for higher order methods, the computations at each step become more complicated. So let's look at an example at the midpoint method, which is a second order numerical method. So in order to get from each step to the next, as you can see, the formula is significantly more complicated. Yn plus 1 is yn plus h times f of x plus xn plus h over 2, and yn plus h over 2 f of xn and yn. So we have to compute the value of the function f 2 times at each step. So we have f of xn and yn, and then we have f of this complicated expression. It turns out that this is a way to match The second order Taylor expansion of the function. So here we use this approximation that f of xn plus h is approximately equal to f of xn plus h f prime of xn, and then we use one more term in the Taylor expansion, so plus h squared over 2 times f double prime of xn. It turns out that this more complicated expression is a way to approximate this second order Taylor expansion. And the error that we make in this approximation will be of size h cubed. So whereas in the Euler's method, the error at each step was of size h squared, here the error at each step is of size h cubed. And in general, if the error at each step is of size h to the n plus 1, then the numerical method will be of order n. So here, because it's of size h cubed, this will be a method of order 2. So let's do one numerical example. Let's consider the same initial value problem. And let's use, so the problem is y prime is x squared minus xy squared with the initial condition y of 2 is equal to minus 1. Let's try to estimate y of 3 using the midpoint method with step size 1/2. So this means we're going to need 2 steps to go from 2 to 3. First we'll go from 2 to 2.5, and then from 2.5 to 3. But the computations at each step will be more complicated. So using the formula on the previous page, so at each step, yn plus 1 is equal to yn plus h times the function applied to xn plus h over 2, and yn plus h over 2 times the function of xn and yn. So this is what I wrote here. The function is, so we have xn plus h over 2 squared. This corresponds to x squared here. And then minus xn plus h over 2 times, and it's going to be, so it's going to be y squared, where y is yn plus h over 2 f of xn and yn. So it's yn plus h over 2 times xn squared minus xn yn squared, everything squared. Okay, so it's a pretty complicated formula. And then when I actually do the computations, I'll do them in 2 steps. So first, let's compute the value, the approximate value of 2.5. So first, I'll compute x0 plus h over 2, which is 2.25, and y0 plus h over 2 f of x0 and y0, which is minus 1 plus, so h over 2 is 0.25. So it's plus 0.25 times 2 squared minus 2 times minus 1 squared, and I get minus 0.5. So then I took these values and plugged them in in f. So it's going to be f of x0 plus h over 2 and this expression y0 plus h over 2 f of x0 and y0. So I use these two values inside of f. Okay, so the computed value, the approximate value is y1 is equal to 1.25. And then from this step, I do one more step. So the next step will be, I start with x1 and y1, and I compute x1 plus h over 2 and y1 plus h over 2 f of x1 and y1. And then I take these values and plug them into the formula for y2. And we get the approximate value 0.396. This is not a very good approximation because the step size 0.5 is much too large. But in any case, this is how the midpoint method works. So there are infinitely many possible second order methods. Let me just mention one more. So in Hume's method, we use this formula yn plus h over 2 times f of xn yn and plus f of xn plus h yn plus h f of xn and yn. So f of xn and yn is what one would use for Euler's method, and f of xn plus h and yn plus h f of xn and yn is pretty much computing one more step in Euler's method. And somehow by taking the average between these two values, then this expression also matches the quadratic approximation f of xn plus h f prime of xn plus h squared over 2 f double prime of xn with an error of size h cubed. So it turns out that by using these sorts of combinations, and as I said, the midpoint method and Hume's method are only two out of infinitely many possibilities, then one can match the next term in the Taylor expansion and thus improve the accuracy from h squared to h cubed at each step. So in some sense, Hume's method and the midpoint method are the best two second order methods because among these infinitely many second order methods, some will require fewer computations than the others. So notice that in Hume's method, we actually only have to compute the value of f twice. There is f of xn and yn, which we compute, and we use here and here. And then there is this f of this more complicated expression. And same for the midpoint method, we only have to compute the value of f twice. There is f here, and there is this more complicated expression. In general, in all the other second order methods, we have to compute the value of f 3 times. So this is why Hume's method and midpoint method are better than the other second order methods. However, the biggest improvement that we could make is by using a higher order method. So For a first-order numerical method, if we want to decrease the error by a factor of 10, we have to use 10 times more steps. But for a fifth-order method, for example, using 10 times as many steps will decrease the error by a factor of 100,000, or at least the error bound by a factor of 100,000. So higher order methods are more complicated and require more computations for each step, but they need fewer steps for the same precision. In practice, fourth order methods and above are used instead of first order or second order methods. So people commonly use fourth order, fifth order methods. Also, another thing that can lead to an improvement is that the step size is usually variable, not fixed. So there are, as I said, ways of estimating the error, and on intervals on which the error looks like it will be larger, the algorithms use more steps. And all of this is done automatically by computers, including the selection of the step size and the selection of the numerical method. Some of the most widely used numerical methods are so-called Runge-Kutta methods. There exist Runge-Kutta methods of any order. And in some sense, all the methods that I have presented so far fall under the category of Runge-Kutta methods. And however, these are some of the best known methods, namely the Runge-Kutta method of order 4 and the Runge-Kutta method of order 5, which I'm not going to present. So this is how a fourth order method looks like. At each step, you have to go from yn to yn plus 1 by adding h times a sum of 4 different terms, which have to be computed separately, involving the values of f at different intermediate points. So fourth order numerical methods really are more complicated than first or second order numerical methods. Again, this is one of the best used and best known numerical methods, and its accuracy is sufficiently good that it can actually be used in practice. Fortunately, as I said, computations are done by computers, so this is just a well-known and almost universally implemented algorithm for numerically solving ordinary differential equations. Okay, I think this is all that I wanted to say in this course about numerical methods. This is pretty much our last course for this semester. I'll continue with some review or extra topics. Thank you for your attention, and see you next time.